precise. Yeah.
Hello, good morning, good evening, good afternoon, everybody, wherever we might be. It's my great pleasure to welcome DEVARSHI MUKHERJEE. He's all the way in Buenos Aires, so hola muchachos. And now he will tell us everything and more about analytic KK theory. DEVARSHI, the Zoom is yours. Take it away.
Thanks, Peter. Thanks for the invitation. It's a pleasure to speak in this seminar. This talk is actually related to the last talk I gave in this seminar, where I spoke about cyclic homology. Today I'll be talking about the K-theory side of things. So it's perfectly set up. Okay. And for me, K-theory is analytic K-theory, or its bivariant version, which is bivariant analytic K-theory. And for me also, my setting is non-Archimedean. So let me start with some motivation. Okay, well, I suppose in an NCG seminar, this part of the motivation is overkill, but I'll still state it. Okay, so the idea is to find a universal functor, or find the universal functor, from some category of algebras to a suitable category which has enough homotopy theory going on in there. And well, it needs to be universal for certain properties. Which are desirable from the viewpoint of non-commutative geometry. Okay, so in this talk, I'll kind of break down what I mean by these things. So the first thing for me, algebras, is algebra objects in the category of complete Bornological ZP modules, which I assume are torsion-free. Okay, so you should think of this as a category which is kind of large enough to contain all limits and co-limits of topological vector spaces. But for me, it's okay if they're ZP modules even. And then I take algebra objects in there. In particular, this contains things like Banach algebras, again, over ZP. Fréchet algebras, and so on. It really contains everything, but I work in this Bornological setup because this has certain very convenient properties which don't exist in the topological framework. For instance, this category has a tensor homojunction, and it's also ideal for homological algebra because it's a quasi-abelian category. So it's really very convenient to work in this framework. Okay, and that's the algebra part. What do I want C to be? Well, that kind of depends on what properties I desire. So the question is, which properties? The properties that I want are homotopy invariance, stability. I'll clarify what stability means in my context, but for now, just think of this as stabilization by some sort of matrix algebras. And excision for semi-split extensions. And by semi-split extensions, I mean extensions of algebras with a bounded linear section. Okay, and the last time I gave a talk here, I talked about analytic cyclic homology, which is a certain functor from the category of algebras to the derived category of inductive systems of Banach spaces over QP. And well, for technical reasons, this has to be projective systems of inductive systems of Banach spaces. So this is analytic cyclic homology. An analytic cyclic homology satisfies these properties. Okay, and where am I now? Another functor which, because it's related to analytic cyclic homology, but that is periodic cyclic homology. This is classically known to satisfy these properties in any Q linear symmetric monoidal category. Okay, and another functor that is very closely related to analytic cyclic homology, and it's kind of known from the C-star algebraic setting as well, is local cyclic homology. Its domain is not quite all Bornological algebras, but a certain subcategory of them, which also includes things like Banach algebras. So this too satisfies these properties. Okay. I'll repeat that. Okay, so these are the properties which we deem desirable. And okay, now about the category C itself. So what do I want C to be? If we see the target of analytic, periodic, and local cyclic homology, this is a certain derived category of some quasi-abelian category, which, but if you don't know what a quasi-abelian category is, it's almost an abelian category, but you have to weaken the assumptions somewhat. There are certain morphisms which are not strict, so you define your extensions relative to strict morphisms or normal morphisms, which are just morphisms where the co-image and the image of every map coincide. Okay, so that's the derived category of some abelian-like category. And this is known to be a triangulated category. So the C that we are after should be a triangulated category. Okay, well, again, if you don't know what a triangulated category is, this is just a category with some distinguished class of extensions such that you have long exact sequences. So that should just remind you of the homotopy category of chain complexes, for instance, and the Popper sequence for bivariant homology. Okay, so that's what we're after. And universality is what you would expect. If you have, well, let us assume we've defined such a functor, then if you have any other such functor, for instance, analytic cyclic homology or periodic cyclic homology into some other triangulated category, then there exists a unique triangulated functor. Right. Okay, now you might ask, why do this? Well, again, in this seminar, this probably needs not much explanation. Well, the role played by bivariant K-theory in C-star algebras is kind of well established. But if you do have such a universal functor, and you have some other functor which satisfies the same properties as, say, bivariant K-theory, then you might also state things like the Baum-Kohn conjecture, UCT for such functors. So what do I mean by that? So in the complex case, C is Kasparov's KK. And let's say if you care about C-star algebras, then let me give this some label. Then X could be local cyclic homology, which is known to be a well-behaved invariant for cyclic for C-star algebras. And D is again a certain homotopy category, which you define for inductive systems of Banach spaces.
And what is the meaning of this local cyclic homology for commutative C-star algebras?
That just gives you sheaf cohomology with coefficients in the complex numbers of the space.
With coefficients in what?
Complex numbers, so just the constant sheaf.
Constant, okay.
Yeah. Okay, so, well, one way to state the Baum-Kohn conjecture, this is in a paper by Ralph May and Richard Ness. Is that, well, let's say F is in the equivariant Kasparov category. You have some morphism from A to B. And its image in KKH of A to B is invertible for all, let's say, compact subgroups. Then F was already a KK equivalence. This is one formulation of the Baum-Kohn conjecture. Okay, now, if this is the case, then that is, if this is the case for some group, then by the universality, of Kasparov's KK, the induced Chern character, which takes values in local cyclic homology or bivariant local cyclic homology, is an equivalence. It's an HL equivalence. Okay, so the point is, if you believe that local cyclic homology is a useful invariant, and it is because it gives you the right results for C-star algebras, then whatever you can state for KK, you can also state for local cyclic homology. Okay, and well, so that's in the complex case. Now, there is also a bivariant K-theory in the algebraic case.
Sorry, just a trivial sanity check. So here, when you say the Baum-Kohn conjecture, you just mean the plain Baum-Kohn conjecture without coefficients, right? And if this implication holds, it means BC holds for this locally compact group G, right?
Yeah.
Okay, just sanity check, okay.
Yeah. Okay, and so yeah, that's the Baum-Kohn conjecture as we know it, but there's also the purely algebraic Baum-Kohn conjecture. So in the purely algebraic case, now what do I mean by the algebraic case? I mean that my category of algebras are really algebra objects in, let's say, complex vector spaces, or I think it just suffices that we have Q linearity. So these are just rings of a field of characteristic 0. In the purely algebraic case, this is due to Willy Cortinius and Andreas Thom. Construct a universal functor, which goes from this category to little kk, which is inspired by Joachim Kunz's little kk for locally convex algebras. And this is universal again for the same properties. And you can, of course, define periodic cyclic homology, which satisfies all these properties in that generality. And let's say this is just in the derived category of pro-vector spaces. Then you can define the bivariant Chern-Kohn character. And again, you can restate the Baum-Kohn conjecture as I stated above in the purely algebraic case. You'd have to replace statements about topological K-theory by homotopy algebraic K-theory, which is the relevant version of K-theory that satisfies all the nice properties, namely accession, stability, and homotopy invariance. Okay, I'll say a bit more about what I mean by homotopy algebraic K-theory. That's kind of the point of this talk. Okay, well, so that's some motivation for why you might want to do bivariant K-theory at all. And well, okay, that's there's more motivation. For instance, you can, in maybe a similar vein, you can talk about the Pimsner-Voculescu sequence. So again, in the algebraic or the C-star algebraic setting, there is an exact triangle in KK. Using the loops on an algebra, so these are the exact triangles in KK. And a cross product algebra by Z, where sigma is an automorphism. So this is the Pimsner-Voculescu sequence. And because it's an exact triangle in KK, again, by the universal property, you get induced triangles. And let's say, if you're working in the C-star algebraic setting, then you get a map in local cyclic homology. So it should shift. And what's the relevance of this? Well, if you know how to compute local cyclic homology for an algebra, then you also know how to compute it for the cross product algebra by the integers. So the point being that you can also compute these invariants by just computing them at the level of KK. Okay, so that's KK. Another motivation for, well, doing non-commutative geometry in this p-adic setting is that you also want a version of K-theory. Sorry?
May I ask you a question?
Sure.
Could you come back to the previous line?
Mm-hmm.
Yeah. You said, no, line, not.
Yeah.
Yeah. you said that this is an exact triangle in KK.
Mhm.
In which sense it's a triangle? Because I see.
Well, in a triangulated category, you specify what triangles are, such as diagrams, which induce long exact sequences. So, I mean, a triangle is just a diagram, and you call a category triangulated if these triangles satisfy certain axioms.
Yeah,
But-
but in a triangle you have
Why
three
don't you just
vertices.
draw a triangle?
well,
There's a triangle.
yeah. Well, at this Pimsner-Vokulescu sequence, this is isomorphic to what you would call distinguished triangles. I will come to that when I really talk about my own type of KK. But yeah, it's isomorphic to a path extension or a path triangle. But at the moment,
in an exact triangle,
Mhm.
you have three vertices, and the fourth map is coming back to the first one with a shift.
Yeah.
Now you have four vertices. What do you mean by this?
Shift is the one
Where-
that the shift is the loop. That is the suspension automorphism.
Yes, but
Loop is the shift.
I understand this. But
Mhm.
then you have A,
Yeah.
and cross product.
Yeah.
So how
I
can
mean,
this come back to A with a shift? Something.
you would rotate it, right? You would rotate the triangle to get a cone extension. You take a map between two algebras, you take a cone object, and then you have a map to the shift.
Mhm.
Yeah, I'll clarify this in my own setting, what I mean by exact triangles.
Okay.
But yeah, you would do kind of what I said.
Okay. Thank you.
Okay, so the second thing we'd like to do is K-theory in this analytic setting. I may temporarily call this analytic K-theory. This, again, should go from the category of algebras into abelian groups for each n. And this should map in the usual sense via Chern character to analytic cyclic homology or local cyclic homology or periodic cyclic homology. And well, you can always define this, but you also want this to be a special case of bivariant K-theory. Just as in the C-star algebraic case, you want to, let's say, once we have defined what a suitable bivariant K-theory is, if we set the first variable to be the ground ring, then you want this to be the analytic K-theory of A. Okay. Right, so this is where we are heading. Now, let me say a bit about the actual construction. And why I want to spend some time on the construction is because you might be more familiar with the kind of Hilbert bimodule picture for bivariant K-theory, but that, at least at the moment, does not make too much sense in the p-adic setting. So, or in the algebraic setting for that matter. So I'm going to talk about a construction which is similar to Kunz's little kk for locally convex algebras, or the Courtenius Thom picture for ordinary algebras. So the construction of KKM. Okay. So just to revisit this, what do we exactly want? We want a functor into some, let's say, triangulated category, which is homotopy invariant. So how do we make sense of homotopies? Okay. So of course, the relevant interval object should be the same as for analytic cyclic homology. That is, they should be homotopy invariant for the same type of homotopy. So what we need is an analog of, if you want continuous homotopies in the C-star algebraic setting, then continuous functions on the unit interval, or if you want smooth homotopies, then smooth functions. But we want this in this p-adic setting. So the analog of this is let me write it and then explain what I mean by it. Okay, so the replacement of smooth functions on the interval is over-convergent analytic functions on a disk. Or if you don't want to use so many words for this, then this is the Monsky-Waschnitzer algebra. So this encodes over-convergent analytic functions. You might ask, why over-convergent and not just convergent power series? Well, that runs into problems if you want to do de Rham theory even. So if you work in the purely smooth commutative setting, then you want some analog of the Poincare lemma, which is that if you take the, let's say, just the affine line, then you might want, if you want a homotopy invariant theory, then you want its de Rham cohomology to vanish in all higher degree. And this does not happen if you work with just analytic functions. So there's that aspect which just goes completely wrong, which defeats the purpose of homotopy invariant theories. So you want over-convergence to even have a well-behaved cyclic homology theory. Strictly speaking, you don't need this. If you can define a bivariant K theory with analytic functions as the interval object, and you can also do K theory in that setting. But at this, well, at least the K theory part has been done by, I think, a student of Karoubi, or it's probably even there in the paper by Karoubi and Bijamajor on KV and KH theories. But for us, because we ultimately want to relate it to some well-behaved cyclic homology theory, these are the right homotopy objects, or the right interval objects, with respect to which we want homotopy invariance. Okay, so now you go from algebras, and you can force homotopy invariance by, well, at the level of objects, there's nothing much that's done, but the home of any two objects gets mapped to the homotopy class. So this is home of AB modulo homotopies, where we say two morphisms are dagger homotopic, if you have a diagram of this form, so you take F and G, and here you take A tensored with this Monsky-Waschnitzer algebra. And you then just take the evaluations at 0 and 1. So you say that two things are dagger homotopic if there is an algebra homomorphism from A to the Monsky-Waschnitzer algebra. This should be a B, of course. Okay, and well, this is not an equivalence relation. You need to take the equivalence relation generated by it, and that gives you the right notion of homotopies. Okay, then the next thing we want is stability. For our purposes, and maybe for the purpose of this talk, we want stability with respect to M infinity. Well, that's not terribly interesting. So we take its p-adic completion. This is already an interesting local Banach algebra. So we want stability with respect to the p-adic completion of M infinity. And well, it's you can of course just force this. So you again define a functor from algebras to the homotopy category of algebras, where again on objects you do nothing, and the morphisms in this category are A and B stabilized with M infinity. Okay. So that's what stability should mean. And we've kind of now forced that our functor that was living in the world of algebras is now homotopy invariant and matricially stable. Right. The next thing we want is accession. And this is obviously where things get a bit more complicated. So here we want an analog of the suspension stable homotopy category. What do these words mean? We want a category in which the non-commutative suspension is the same as the suspension. This is kind of what we want to force. And let's see how that's done. What this uses is, first of all, to define this suspension stable homotopy category. What we need is the universal extension. So the universal extension is defined as follows. Okay, so given an algebra, we define the tensor algebra or the completed tensor algebra as this infinite direct sum, where we take the completed tensor product. And this extension is universal in the following sense. You take the kernel of the canonical projection to A, and if you have any other semi-split extension, then by the universal property of the tensor algebra, you can complete this diagram like this. And the map here is called the classifying map for the extension. Now this lift from the tensor algebra to E would depend on a choice of section, of course. But if you vary the sections, then you get homotopic classifying maps. So these things are unique up to homotopy. Okay. Right. Now we want to apply this to the path extension, which I define as follows. Well, it's probably called the loop extension. Let me define it. Okay. How is this defined? You start with the base loop extension, so to say, and this is defined by the following. Okay, so here you have just the evaluation by 1, and you take its kernel. So this really gives you an extension of complete Bornological algebras. And then you tensor with any other complete torsion-free Bornological algebra. What you get is, well, in this notation, it's loops on B with paths on B and B over here. Okay, so this is a semi-split extension. And now if you take a morphism from A to B, which is living in the world of algebras, and therefore in the world of the homotopy category of algebras, then by the uniqueness of the classifying map up to homotopy, you get a map from J of A to the loops on B. And you can iterate this construction. Well, when you iterate this construction, you get an inductive system of maps of algebra homomorphisms. And if you take the co-limit, then you get the analytic KK of A and B. So you take the co-limit over N of suspension stable homotopies. Okay, so that's this bivariant analytic KK theory. Well, let me just explain some analogies. We did nothing, we just did the analog of what goes on also in the complex or the C-star algebraic world. In the C-star algebraic world, this extension that I wrote down here, this is just the usual, well, I don't know what it's called, but I can define it here. This is C0 functions on the open interval to C0 functions on the half open interval to B. And this is again just evaluation at 1, and this is the kernel of the evaluation map. So this is just the analog of what goes on maybe in the world that you know. Again, if you do the exact same thing, you get Kunz's little kk. And in the algebraic setting, you'd really have to do something like this. And then you get algebraic kk. So the only thing that has changed is the homotopy type and what we mean by matrix algebras. Okay, well, but I was talking about excision. So the question is, what does any of this have to do with excision? And now I invoke that this is a triangulated category. And so for this, I have to specify what the extensions are. The extensions are exactly these loops, paths, and an algebra homomorphism. So this is the cone extension, where what do I mean by P of f? What you do is you take the path extension of P and you take some algebra homomorphism, and then you simply take its pullback. And this is still a semi-split extension. So your exact triangles are exactly maps like this. So with these as exact triangles, and triangulated categories have long exact sequences. So the question is
just a completely dummy question. So how is it a triangle? What you marked in this loop circled up? How is it a triangle?
what do you mean?
Well, isn't it when you have this diagram for exact triangles, you do have a diagram which looks like a triangle, and here I don't see a triangle. I have omega b, pf, a and b. How is it a triangle? Just a dummy question. I'm confused.
I'm not sure why these are called triangles, but you have three things, and then you have
Okay, so triangles are not triangles. Okay. Okay.
yeah, I mean, at least not in any way I could justify right now, but you always have, I mean, if I rotated this, which is part of the axioms of a triangulated category, what I would take is, let me say this for chain complexes. If you have a chain complex and you take its cone, this is just the cone of a chain complex.
Mm-hmm.
And here you just shift it by one.
Yes.
These would be the distinguished triangles for the triangulated category structure on the homotopy category of chain complexes. I mean, I'm poorly educated on why they're called triangles, but I suppose if you localize a triangulated category, the morphisms really are triangles.
Yeah, that's what I would guess. Tomek, you have a question?
So you have
yes.
zigzags like this.
So coming back to this Pincer Voiculescu.
Yeah.
So this is obviously a triangle, what we are showing now.
Yeah.
But I have a problem with this previous triangle 2B, which starts with omega A and ends up with the cross product. What about some relation between omega of A and
the cross product.
And the cross product, yes. So something is hidden here.
Yeah, well, I mean, I can give you the kind of reference for this, but it would appear as a cone of a certain map. This is
so you are using, okay, so you are relating this omega of A with this cross product via some cone.
Yeah, it would be the
Yeah.
cone construction in the category of C-star algebras. Yeah.
Okay, now I see. Thank you very much.
I mean, it's not on the nose, I suppose. You'll have to. It's technical to prove the Pinson of a Fulescu sequence.
There must be something technical.
Yeah.
Okay, thank you.
Okay, so now what we want to talk about is excision finally. So if we have a semi-split extension, again, by abstract nonsense, we get the classifying map. From J of C to I. Call this gamma. And this induces a triangle. Where we take J of C, I, B, and C. And here I take P of pi. Well, okay, now this is kind of where all the complexity is hidden. In KK, this is really the same as loops. As I mentioned, this is kind of what we need to aim. And then you really get an honest triangle and not these, not the non-commutative suspension. So this equivalence is in KK. And so there's some work to show that this J of C, which you get by just kind of taking the universal extension, this ends up being the same thing as loops on C. Okay, now we're not done yet. We need to show that this triangle, this induced triangle from a semi-split extension to what we are actually calling a distinguished triangle, this is the same in KK. This is something we want. So what we need to essentially build is this map from I to P of pi. And this needs to be a KK equivalence. And once that is the case, we're done. So what is this map? Well, in one direction, this is just the inclusion into the second summand. That's this map I. Where, well, recall that P of pi was just the pullback of the projection. So there is an inclusion of the kernel into the pullback. And explicitly, it's just x going to 0, x. Okay. So this is a map in one direction. In the other direction, the map from J of P pi to, let me abuse notation slightly here and call it loops on I. Well, you get such a map as loops on I into the pullback of P to P of pi is a semi-split extension. So what we get is a map like this, as this is a semi-split extension. Okay, but you get a map from J of P of pi to loops on I. So you don't get an on-the-nose inverse, but in KK, your maps are defined as J of something to loops on your target algebra. So this ends up being a KK equivalence. Let's say this more accurately. So if you call this one alpha and you call this one beta, then alpha and beta are KK inverse to each other. Okay, so what have I done in this entire thing? I started with a semi-split extension, and I showed that the induced diagram is in the category KK the same as a distinguished triangle. And therefore it has long, well, any triangulated category has long exact sequences. So if you plug in some target algebra, then you get, well, the Popper sequence in KK. So this leads to excision in KK. Okay, so just to summarize what we've done.
May I ask you a question?
Sure.
Is this construction related somehow to Bott periodicity?
In the complex setting, yes, but I was going to make a remark on that later. You don't expect to have Bott periodicity in either algebraic KK or analytic KK. There's no intrinsic periodicity. But I'll make a remark on that later. But in the complex case, most definitely this is related to Bott periodicity.
Okay.
Okay. Right. So what have we done? We have constructed a functor from the category of complete torsion-free Bornological algebras to this category that we built. And this functor is homotopy invariant, stable, and excisive. Oops. Okay, and well, again, just for abstract nonsense, the way we built this is that if you have any other triangulated category, then you get the universal property that we were after. And well, this unique functor is just the identity on objects. Or, well, it's not the identity on objects, but whatever this x is, this x tilde will be the same on objects. Okay, so that's analytic bivariant K-theory. Now let's discuss some consequences of this. Okay, now this is again analogous to what happens in the C-star algebraic world. You get a bivariant Chern character into analytic cyclic bivariant analytic cyclic homology. You also get bivariant Chern characters into periodic cyclic homology. This factors through HA. But there's something more that's going on in the p-adic world, which is really unique to this setting only. And what is that? You can talk about the reduction mod P of an algebra over the p-adic integers. So you can mod by P. And there is a map from KKN of AB to KK of the reduction mod P. And this is just the algebraic KK, which is by Willy Cortinius and Thom. And there is also a version of analytic cyclic homology for algebras in the torsion case, that is for algebras over a finite field. And again, by the universality of algebraic bivariant K theory, you get a map from the reduction mod P's to these. And in appropriate cases, this is an isomorphism. So what you've done is, let me first say in appropriate cases, there's a small technical assumption that goes on here for when the reduction mod P is an isomorphism, which I'll come to shortly. But okay, let's assume we know what this appropriate case is. We then have these bivariant Chern characters on FP algebras, or the bivariant K theory of FP algebras, all the way to periodic cyclic homology. So in some sense, what you've done is you've lifted Chern characters which live in the finite field world to QP vector spaces. And this is kind of unique to this p-adic setting. You can mix characteristics. Okay, so that's one consequence of the universal properties of KK. Another thing is you can now specialize to the case where A is ZP. And what you get is something that I call analytic K theory. Well, I suppose. Okay, well. And this maps into analytic cyclic homology. Well, I'm just specializing the diagram 1 to the case where A is FP. And this is kind of the analog of the usual Chern character. And again, the same thing goes on downstairs, where KK, algebraic KK of FP with coefficients into B. This is an important theorem due to Cortinius form. This is the homotopy algebraic K theory of B mod P. Okay, now let me address when this is an isomorphism. This happens, well, under a very mild condition. That is, the reduction mod P, this map, well, it should map bounded sets to finitely generated submodules. Subspaces. And well, when does this happen? This happens when the algebra B is nuclear. And there's a way that, well, in a recent paper, we discuss how to exactly turn any Bornological algebra into a nuclear one. And what we do is we equip it with the so-called pre-compact Bornology. So you take, say, a Banach algebra. There is a way to, there's a functorial way to equip it with a Bornology such that it lands in nuclear ZP algebras. And that functor is just the pre-compact Bornology functor. So that's just a technical thing to tell you when this map is an isomorphism. But when you do have such a nuclear algebra with the right growth properties, such as the Monsky-Waschnitzer type of algebras, then this is an isomorphism. In particular, if you take a Banach algebra and you do this Bornological process, then you get an isomorphism.
I'm sorry, can you remind me what the nuclear ZP algebras mean? I know usual nuclear sister algebras, but how about the ZP algebras?
Well, it's a Bornological condition, which I was sweeping under the rug. An alternative characterization of it is that its reduction mod P is this. This is an alternative characterization, which I can just state off the hand without defining too many things. It's just a Bornology on a, let's say, torsion-free ZP algebra, such that when you take its reduction mod P of any bounded submodule, you get a finitely generated submodule. But if the details of this entire construction is in a recent paper with Ralph called Local Cyclic Homology.
Yeah, I mean, please forgive me my ignorance, but so how does it relate with the usual characterization of nuclearity? That's what I fail to see.
Well, there is a characterization where you can take an algebra, and if you tensor it with the Hom, you can bring the Hom inside. This just happens to be the case also for these algebras.
Ah, okay.
So it recovers the known thing for complex Bornological algebras. Yeah. Okay. Right. Okay. So we have these Chern characters which are related to the Chern characters mod P in this way. And well, one might now ask, when is this the case? Do you have that, whatever this K theory is it the same as its reduction mod P? And that is something I will come to in just a second, but let me describe a third consequence again of just these formal properties. But the second thing wasn't really a consequence, was more a specialization, but the third one is definitely a consequence. Now, take this map from Kn of an algebra to periodic cyclic homology of an algebra tensored with QP. Now, when A is smooth and commutative, then this side, by just, well, by the usual argument for, let's say, algebraic varieties over the complex numbers, this ends up being the same as, this ends up being the same as the periodification of de Rham cohomology. And de Rham cohomology in this setting is called rigid cohomology. So n plus 2j of the reduction mod P coefficients in QP. So this is, well, this is just the algebraic de Rham complex defined using appropriate growth conditions. Okay, so what you get is the usual Chern character from K theory to de Rham cohomology. This is the analog of of, well, the usual Chern character from, let's say, the K-theory of smooth this is diffeotopy K-theory, smooth functions on a manifold into periodified de Rham cohomology. Okay, so these are just consequences of the existence and certain computations of periodic cyclic homology. Okay, but so far I've not really defined analytic K-theory. I've just said that it is just a specialization, and it turns out to be isomorphic to something, and that something is what I'm going to define now. Okay, so analytic K-theory. Okay, so the easiest or the quickest way to define this would be as follows. You define this to be a certain co-limit of K0 groups. Where this sigma is, it's the KK inverse of the loop functor. But more concretely, this is defined as follows. It is the quotient of a certain cone ring by M infinity. This is Karoubi's cone ring. Oh, it's the p-adic completion of Karoubi's cone ring. If you don't know what these things are, then just think of this as the quotient sitting in the Kalkin extension. So if you take the compact operators on L2, sitting inside bounded operators on L2, and you get some Q of L2. So this object is analogous to this object in the algebraic setting. Okay, but for the purposes of K-theory, this is inverse to the loop construction. Okay, so you get some diagram involving the K-theory of the suspension and the loops, and you take its co-limit, and this defines analytic K-theory. So this is just the quickest way to define it. One can, of course, define this as you take the non-connective algebraic K-theory spectrum, where you define, well, you have to homotopize it using these dagger homotopies, and then you have to check that these things really work. But that would be the more conceptual way of doing it. But okay, this is just an off-the-hand definition that I can give you of analytic K-theory. And this functor is so this functor is dagger homotopy invariant, and excisive. Now, you'll need to stabilize it. So this is what I call stabilized analytic K-theory, where this is just the analytic K-theory of a tensor with M infinity. Okay, then K tilde is also stable, in addition to being homotopy invariant and excisive. Okay. Right. Now getting back to this point about what happens to this side, whether this is also just the same as the reduction mod P. This is indeed the case. So the comparison with KH. I mean, we need to see why we exactly want something like this. This is somewhat of an additional feature of the non-Archimedean setting. Since I also mentioned this local cyclic homology paper, what we showed is that local cyclic homology kind of, by the way it's defined, only depends on its reduction mod P. Which is to say that if I take the local cyclic homology of, say, a Banach algebra, this is the analytic cyclic homology of the reduction mod P. And this is without any Bornological assumption. But again, the Bornological assumptions are in the definition of this functor. But the point is, it only depends on its reduction mod P. So the question is the stabilized analytic K-theory also just the homotopy algebraic K-theory of the reduction mod P? And again, under a mild assumption, which is probably something one can get rid of, but I haven't really looked into that. If you have, let's say, R is a torsion-free ZP algebra, such that its dagger completion is contained in its p-adic completion, then this is indeed the case. And this is the same as KH. Oops. Of R mod P, and this is the same as K and tilde dagger of the p-adic completion. Okay, so in other words, this goes by the name Karoubi's density.
Go ahead, Tomek.
I have a question.
Yeah.
Could you remind me the general relation between the dagger completion and the p-adic completion? What could we expect in general?
Yeah, I'll maybe let me do that by example. So when do the hypotheses of this hold? Let's take just the affine line. Let's say this is my R. Then R hat would just be convergent power series. And our dagger would be over convergent power series. So the valuation of this grows linearly in N. So it's more than just convergence, as justified by the name. In this case, it's really included in this. We've also checked, and well, in general, this is true for any commutative finite type, let's say. So under reasonable assumptions, this is true for all commutative algebras of a ZP. So let me state that in some generality. Affinoid dagger algebras are contained in quotients of Tate algebras. This is the generality, but it's an on-the-nose inclusion. For non-commutative things, the difficulty is that this dagger complete, you need some work to really compute the dagger completion. It does not follow for purely formal reasons that the dagger completion is contained in the p-adic completion. But maybe I can say some words about maybe some reminders on what the dagger completion even is in the non-commutative setting. In the non-commutative setting, let's say R is a Bornological ZP algebra. Bornological means that it has some bounded sets, and in order to, what we need to do is enlarge the Bornology on R to get these larger dagger algebras. And how do we enlarge it? We take growths precisely of the kind we need. So if you take the Bornology then generated by such submodules, then, okay, this is a Bornology on R, completing in this Bornology gives you dagger algebras. So when is it precisely going to be contained in the p-adic completion? You'll have to actually compute the dagger completion and see if it is included in R. It might be possible to just get rid of this assumption altogether. Maybe it already suffices that R is contained in its p-adic completion. Then it's possibly true that R dagger is also contained in R hat. This sounds very plausible. And this is something you can check without actually computing the dagger completion. So checkable. Okay. So yeah, that was the interlude on dagger algebras. Okay, but whenever you have this condition that R dagger is contained in R hat, you have a Karoubi density theorem. That is the analytic K-theory of some smooth subalgebra of the p-adic completion is the same as the K-theory of the p-adic completion, and that ends up being the same as the reduction mode P. Why I call this Karoubi's density theorem is that because this was checked for what is called the KV theory. So this is a classical result that's known about the Karoubi-Wijama theory. Okay, so that's analytic K-theory. And let me just conclude with some final remarks. So in general, K and dagger carries more information than cyclic homology, HA or HP or HL. And the reason is, as we were discussing, this is to do with Bott periodicity. There is no intrinsic Bott periodicity on the analytic K-theory side. You can kind of force this by periodifying it. But on the other hand, these theories are intrinsically periodic. They're too periodic. So it need not be, there is really information in each of these K-theory groups for every integer n. Also the negative ones. So in general, I would expect this to carry more information. But what could happen is that if you, let's say, periodify them, and if you rationalize them, that is, I think the more important thing is rationalizing. Might end up killing a lot of this information. And well, what do I mean by this? If you just take the case of the finite field with p elements, the algebraic K-theory computation of this is known, and what you get, well, in degree 0, you just get the integers. And if you rationalize that with QP, that is, if you tensor over Z with QP, you just get QP, obviously. And that is the same as the analytic cyclic homology at degree 0 of ZP. Okay, so far, or the analytic cyclic homology also of FP. So let me just write that down. Explicitly, this is just QP in degree 0. But if you now take higher K theory, this computation is known, it's due to Quillen. What you get is, well, in even degrees, you just get 0. In odd degrees, you get torsion subgroups. That is, you get groups which have torsion. I think it's something like this. So I odd. These are the algebraic K-theory groups in odd degrees. Now, if you rationalize these, a lot of them, well, they just disappear. So for that reason, it could still be the case that for algebras A in a, let me call it bootstrap class, some periodification rationalized with QP is isomorphic to HAN of A. And yeah, I suppose we'll have to take some sort of product periodification of this. Okay, and this would recover the known result about local cyclic homology in the C-star algebraic case. That is, if you take topological K-theory of A and rationalize it, and that's the same thing as the local cyclic homology of A for all n. Okay, but that is something that needs to be checked. What also needs to be kind of worked on is what I mean by the bootstrap class. So in the minutes that remain, what is the bootstrap class? For in the C-star algebraic setting, this is a certain subcategory of separable C-star algebras which are generated by kind of all the triangulated category axioms. So you take suspensions. So in separable C-star algebras, you take subcategory generated by suspensions, KK equivalences, mapping cones, and the fourth thing, which is countable direct sums. And this kind of gives you this gives you a very large bootstrap class. And this is the definition of the bootstrap class in Kasparov's KK. KK for separable C-star algebras. Okay, now we can do the first three things pretty easily even in the algebraic setting, but there's a slight problem with countable direct sums, which is a kind of inherited problem also from Kunz's little KK, which is that countable direct sums need not exist. There's no reason why they should exist. And let me give you a heuristic reason for that. Well, if you see the definition here, then if they were to exist, you should be able to pull out the direct sum from this summand, but that would require it to commute with these JNs, and JNs are kernels in the category of algebras. And there's no reason why these should commute with countable direct sums.
Sorry, just a stupid question. How about finite direct sums?
Those exist. That should be fine.
That's infinity, which is a problem.
It's the infinite direct sums that's the problem. So the resulting problem, if you work with variants of little kk, is that the bootstrap class, if defined this way, would be rather small. Or it's unclear at the moment what the bootstrap class even is when you don't have countable direct sums. You can of course just define it to be the first three things, but there's just no reason why it should be large enough to do anything meaningful. So one might have to.
Sorry. You didn't write what this class is generated by. Through this operation.
Well, you take just the complex numbers.
Okay.
Mm-hmm.
So wait, yeah, another way of defining this is that it's the triangulated, or maybe the tensor triangulated category generated by the ground ring.
Yeah, there is a question. Please go ahead.
Yeah, I was wondering if you could define the triangulated category as the homotopy category of some type of model category that would be based on the type of non-commutative rigid analytic space. So like a one homotopy theory, for example, and then you would have arbitrary, sums, but then you would have to mod out by the appropriate relations that you have to invert. Would that work?
It could. I have seen results in this direction in the in the C-star algebraic setting. So it could work. I haven't tried it, but yeah, we could talk about this later.
Okay, thanks.
Yeah. But yeah, I mean, maybe so while you introduced, you said analytic KK and beyond. This is the kind of beyond stuff that we are discussing at the moment. One thing that is worth a try is you take the int completion, then it has everything by default. It is still a triangulated category, but again, this functor need not, the direct sums that exist in this int category need not be the direct sums of the category of algebras. So what you would then have to do is you'd also have to take the int completion of algebras, which is something which also shows up in the construction of KK. I hid that, but they kind of show up and then they disappear once you take colimits, but it might make sense to work with inductive systems of algebras throughout. And then if you extend this functor, this universal functor, then this resulting functor might end up having the right properties. Well, it kind of by construction preserves colimits. What you would then have to see is whether you can still use this bootstrap class for meaningful computations, and maybe the most meaningful one would be to have some analog of this result. So that is where I am at the moment. But I think up until these final remarks, up until I think this remark, everything is in this preprint that I uploaded a couple of months ago. Okay, and I would like to stop there. Thank you for your attention.
Muchas gracias. Okay, any further questions? Richard, how about you? It was your idea.
Okay, maybe one comment. So the point of bootstrap class is that you should have some kind of UCT.
Yeah.
If you take this incompletion, things break down. Very simply. Just won't work.
Right.
It's not so simply for KK. Because
yeah,
incompletion will produce things like group C-star algebras.
Right.
Non-amenable groups. Okay, so UCT will not hold.
Right. No, but I'm also okay if they work for amenable groups. Because if you take the group C-star algebra of an amenable group,
but you don't have the incompletion will lead you to others. No, problem is not that group X, it's group C-star algebra.
Yeah, I mean, that is, of course, it's
so
how do you use
such
that incompletion? Yeah,
right?
Yeah, sure.
So incompletion is a bit too much. That's why it's separable with countable direct subspace.
Yeah.
So actually, you shouldn't, if you want your class, you don't want to define it as a bootstrap class in this sense, right? You rather want to define it as the class for which something like UCT holds.
Right. Yeah.
Okay?
Yeah, I mean.
And then you can ask what it is.
Exactly. Yeah.
And there's one comment, there's this triangle thing.
Uh-huh.
You do me a favor, draw a triangle. Okay, I'll tell you what to draw. Start. A, arrow to A. Just do it. Arrow to A. No. Going horizontal arrow.
Horizontal arrow to A.
Yeah.
Okay.
A at the other end, yeah.
Yeah.
Now the arrow on the A on the right, arrow down left.
Yes.
Down left, like
Okay,
this.
arrow, yes.
Yeah.
Right A cross Z.
Yeah.
Yeah, and then draw arrow from A cross Z to the left hand A. And add one in square parenthesis, well, one of this vertical arrow, one of this vertical arrow. Okay,
Uh-huh.
just one in square parenthesis next to one. No, not this one.
Then
Any one of the others, not this one.
this one.
For example, yes,
Uh-huh.
but in square parenthesis, degree shift.
Degree shift where?
Here, just this one in square parenthesis. Add square parenthesis around this one. That's your triangle. And that's your that's what you wrote.
Right.
And the arrow up, the arrow between A's is 1 minus alpha. Okay, and there's the triangle.
Right, right.
And I guess it's exact triangle.
It's exact triangle, yes. So the proof is that this is exact triangle, right?
Yeah.
So it's saying, so Pinsen-Forculescu theorem says that this is exact triangle.
Exact triangle, yeah.
Okay.
Okay, and in fact,
Okay.
In fact, in what you draw,
In KK.
there was omega. So my question.
That's the
was
shift,
about-
right?
That's the shift. Yeah.
That's
Yeah,
the shift. So it's infinite sequence. Well, there's a shift, right? From A cross Z to well, how is it? So let's say omega A. Right? The map is actually from A cross Z to omega A.
Yeah.
Okay. So the shift of A. So think A is actually, there is a shift on your category. Given by suspension. Omega is the inverse of suspension.
Yeah.
Yeah.
It's an
So
equivalence on your category.
this was my point. That
What?
this cross product should go to this omega of A.
So,
No, but you can always shift that. You can you either map from the cone to the shift, or you map from the shift to the first three vertices.
Yeah, but in your drawing, I remember it was omega A goes to A, next goes to A through 1 minus this automorphism. Yeah, if you could come back.
Oh, yeah, you missed it. Oh. Here.
no, that's not the triangle.
Not
Yeah.
this one. Not this one. No,
About. But it's the circled one, no?
no.
This one, yeah.
Yes, it's here. It's here. Okay. So it is.
Yeah, it
not
should
this.
be actually omega because
Yeah. Okay.
So this was my point.
Okay. Thanks. Okay.
Okay, anybody else? Adam?
I have.
No, I don't have any question.
Okay. Tomek?
Yes, I have a question. If you think about the reduction module of P, then by functionality, everything is acted on by the Frobenius. And then you
In
have
the
this
commutative case,
predicting
yeah.
of the term character. So I wonder what happens to Frobenius if you leave to zero characteristic to PI.
Yeah, that's a good question. It's I haven't looked into it yet, but that was kind of one of the reasons for doing this analytic cyclic homology in the first place. But yeah, this is a good question. I don't have an answer right now. Yeah.
All right, anybody else? You guys are happy? Okay. I don't see any other volunteers, no raised hands. So let us thank our speaker again. Thank you so much, Marty.
Thanks for having me.
So let me stop recording.